Today's agenda, sorry, good morning everyone. We'll go ahead and get started. Um, Today's agenda, do a review of create and alter statements, the DDL statements, which you guys are using in Lab 7. We left out talking about storage management and partition tables. We'll spend time on that today. Then we'll talk about creating indexes. So let's go ahead and get started. So creating tables, creating things in the database. These are the 5 things we can create in a database: table, view, sequence, index, and synonyms. Last time we had talked about table, sequence, and synonym. We have talked about views before when going through SQL statements. So this is what a create table statement looks like. Providing column names and the data types. And there are 4 common data types you're going to end up using: number, date, and varchar. In fact, those 3 are the most common ones. We then talked about different types of constraints. We talked about different types of constraints. And sorry, just trying to get to the 5 types. Some of these can be defined at column level and some at table level. Not null is always defined at column level. The other 4 can be either defined at column or table level. So this is how constraints are defined at table level. We have constraint name, the type, and then the columns involved. There are 2 ways to go about defining the database schema. So there are 2 ways of going about defining the schema, and one is you can first the first thing we can do is create all the tables and respective columns. And then the second thing is alter the table to add constraints as needed. Or alternatively, I mean, this is one method. The second method can just be create statement that includes column and constraint definitions. And you should put this in a script with drop table commands on the top. A reference to use is the one from assignment 2. So if you go under assignment 2 and creating a script like this is what I'm looking for. So obviously the insert statements will be added in lab 7. Excuse me, lab 8, not lab 7. Lab 7 is what you're working on now. So right here, this is the text file. You can open it locally as well. And the link is under assignment 2 right there. You ran this following script. You ran that script when you started with assignment 2. Any questions on the material covered last time? Okay, so let's start talking about advanced concepts. So we'll get into creating tablespace and then partition tables, and also talk about storage management. This is where you guys are going to learn a little bit of the database architecture. So creating a table space. So let's first visualize how the storage is organized in the database. So storage in a database, we have a concept of a table space. This is a logical idea which contains a bunch of data files. When I say logical, that means it physically does not exist in the database. Data files are physical aspects on the file system, and we take a sequence of these data files and make an entry in the data dictionary to say that each file with a gig of storage will give us a total of storage space that we need for a database. One database can have multiple table spaces. Then each data file is organized into segments, extents, and blocks. So these storage units help for making the storage management in a database. Block is the smallest unit or the smallest currency that we use in storage when we need the, so like pennies is the smallest unit of currency in US dollars. Blocks is the smallest unit. Each block makes, a group of blocks will make a segment, a group of a group of blocks will make an extent, a group of extents makes a segment. There are different types of segments depending on the type that we want to use the storage for. You guys are also somewhat familiar with crow notation. So this is a logical and physical view of data storage and management. As you can see, one database can have multiple table spaces to segments to extents and blocks. If you see the correspondence between row and block, one row can be stored in many blocks, or vice versa, one block can have many rows stored in it. The correlation between the physical and logical view is that one data file can be part of one table space, and one data file will have many blocks, and it's likely that one Oracle block is equal to one OS block, or one Oracle block can have many OS blocks. These are the different type of segments where data is where data is used. So when we are trying to create a table, a cluster, or a data partition, we use application segments. Then we have system segments, rollback, temporary, and bootstrap type segments. So the idea is that segments define how the data storage is utilized. Everything at the end of the day is organized in table spaces. We have initial, next, PCT increase, min and max extend as storage parameters. So when we allocate a unit of storage, we set up an initial size when the storage is allocated in a segment. Each time there is an increase, we use the next extent. The next extent size defines the starting size of each subsequent extent. Then PCT increase can either remain at 0, or if we expect increase in storage over time, we can make this exponential. So each time an extent is allocated, we can increase the percent size. So if we say increase it by 5% or 10%, then each time a new extent is allocated, we can make the growth exponential versus linear. And we can cap out the storage by setting up max extents. So storage management clause is used like this in the create table. This is just again for informational purposes. You guys don't have the ability to create a table space in the database, so you won't be able to practice the storage clause or the create table space clause. So the storage clause that I just showed you, this thing right here, can be allocated at either when you create the table space or create a table. There is also the idea of a default storage clause, which is added in the create table space command, which will be used. So instead of specifying a storage clause in each table, if a default storage clause is applied, then each time an object is created, it sets the default properties for the table. And blocks and extents are allocated when the segment is allocated. When we look at a data block, it has header, free space, and data. This is how these two parameters are used, PCT free and PCT used. These are two additional parameters in the storage clause. PCT free refers to the percentage amount that should remain free in a data block. So what that means is we can continue inserting data in a data block until it's 80% used or 20% remains free. PCT used, when it's set to 40, that means that if a data block is at 80% usage and the rows expand internally, meaning new columns are added or so on, then the block utilization will go above 80%. And we will not be able to add new data in a block unless the percent used falls below 40%. So no new inserts are accepted until such time that the PCT used value or percent used falls below 40%, at which time new inserts can be done in the data block. This is an artifact that is managed by the database automatically today. It's basically managing each block for storage. There are a series of storage clause data dictionaries that allow preview into the data associated with storage, whether it is data files, segments, extents, or otherwise. All of this is background information and storage management that you should glance through these slides and just make sure that at a high level you understand these concepts. So now that we have gone through these ideas, we can talk about how a table space is actually created. So creating table spaces. As mentioned earlier, table space is a concept that's basically a logical idea that is used for storing elements in the database. So the way we create a table space is we use the create tablespace command, the DDL create tablespace command. So we specify the name of the table space. We can specify unlimited number of data files. And we can then provide information on the storage parameters. How many minimum extents, block size, and so on. This is an excerpt from Oracle documentation. These are some examples of how table spaces are created. Like in the first one, we are going to create a undo table space. That is basically a temporary table space which can be used for storing data associated with query processing. We specify a data file name, we specify a size, and then we say auto extend on, which means that if the size of the table space needs to be increased, can be done on demand. The second example shows that we create a table space named TBS01 with an initial data file of 20 megabytes, and we provide the default storage clause. So we specify initial, next, min extents and max extents values. We can take a table space online or offline. If a table space is online, that means it's ready for use. If it's not, it's offline, meaning we may be using it for backup, etc. So as you can see, there are several examples, each using a different part of the create table syntax, create tablespace syntax. We can say things like extent management local, which means that extents that are associated with a tablespace will only be used by the one tablespace. Otherwise, if not, extents can be switched between tablespaces. If we say space management auto, the block management is automated with the idea that I covered earlier of PCT free and used. So when space management is automated, the blocks come off the free list or get on the free list automatically based on the values that are set in PCT free and PCT used. Turning auto extend on in our table space. What does that mean? We usually want to turn this on so we never run out of space in a database. We can also specify minimum extent size. So these are all showing different ways of different examples of a fairly complex create table space statement. So once you're familiar with the idea of storage management and table space creation, what you have to do is work with creating database partitioning. This is something that is expected for usage in Lab 7 from you all. So data partitioning is the ability to break the table and indexes down into smaller manageable chunks. Why do we want to do that? So we can create significantly large databases to work with. So the idea of data partitioning is to organize the data. It's to organize the data into smaller manageable chunks. So there are different ways that we do that depending on the data type of the columns in the database. So when a table is partitioned, the queries can be faster because you're looking through a smaller data set. And partitions are generally, it's a logical idea, but they can have some physical attributes. And those physical attributes are defined for objects that are stored within within the partition. So what is stored in a partition is rows. So when we define physical properties for a row, then we are basically saying how those blocks should be, for that partition should be treated. So like we have table spaces in which we save objects, we have a similar idea of a data partition for saving rows. So here is an example of how data partitioning can be used. So you can have your create table clause, then you can have a partition clause. In a partition clause, we can say the partition type and how the partitioning will be implemented. If you are dealing with numbers, like if the column type is the number column, then we can say values less than in a partitioning type called range. So in this case, basically, if we say value less than 100 in column 1, then all rows where column 1 value is less than 100 will go in partition 1. All values less than between 101 and 200 can go in partition 2 and so on. So what we are starting to do is improve the data storage by doing a little bit of load balancing between data partitions. Obviously, as a result of setting up the data this way, you can figure out that the backup and recovery is also improved because we can now back up one partition at a time. So it will allow for better I/O when we start using data partitioning. So we talk about these different types of partitionings that you can look at for lab 7. We have 3 basic ones: range, hash, and list. And composite is a combination of those. This is partition by range. Here you set up a series of columns. You can specify up to 32 columns into partition by range here. And then you use the range values clause, which is seen here. Like we basically say value less than, as I showed you a little bit earlier. So here is an example that will clarify the usage of partition by range. So partition by range can be used with the number and date data type. So when we use time ID, which is a date data type, we can say values less than 1st of April 98 will go in Q1 of 98, then Q2 of 98 and so on. So hopefully by now you can see how the data is broken down into smaller partitions. So if I'm doing a query, say for date range of month of May 98, then I'm going to look in this Q2 partition. As a result, I'm looking at a smaller data set for the range of data rather than looking at the entire table. That in itself will improve the query performance. Another partition type is called lazy partitioning, also called partition by hash. In this, we can basically specify the number of partitions and the database will do the data partitioning. We use hash partitioning if we are using one if you're searching for one or two values at a time. So it works well with column data types that are either number or date. So you can see in the bottom left of your screen, we have the product ID and we specify 5 partitions. So what happens is each time a product is saved in the database, we look at the product ID and based on the hashing algorithm, it automatically decides which partition to save the data in. And once the data is saved, it can retrieve that back. So if we are trying to get a range of values and use hash partitioning, it will be very slow. But if we are fetching one or two values, partition by hash is going to be very, very useful. Hashing algorithm that's implemented in Oracle is called linear hashing. So as long as we have number of partitions that are 2n plus 1, 2 to the power of n plus 1 will basically get good performance. Then we have list partitioning, which is dealing with a range of a bunch of strings. So we specify the column type in this case, that is usually a varchar or varchar2, and it kind of looks like this. So we have partition by list and we use the NLS territory or the name of the country to specify the partition. So we name the partitions Asia, Europe, etc. and start defining names of the countries for each partition. Then our next type is composite partitioning, where we combine the different partition types: range, list, or hash. Something like this, where we can have partition by range and subpartition by list. So we specify credit limit for range and NLS territory for list. By creating a subpartition template, we are basically saying we are going to use these three partitions for each partition: P1, P2, and P3. So what you would want to do, folks, is take time to get to know the syntax for each one of these partition types. Here is one example of composite hash. Here we partition by range and then subpartition by hash. So we've got a bunch of partitions, and sometimes we say we may want to break that into subpartitions. We can either just say number of subpartitions we want, or we can name the subpartitions. So Oracle provides high availability as a result of using data partitioning. Because when the data is broken down into different partitions, we can take one partition offline to enable the usage of we can take like one partition offline to back up while the rest of the database is available for usage. We have two types of clusters in Oracle. Table, we have a table cluster or a column cluster. And the one we are talking about here is column cluster. So like we'll have a common primary key between three different tables. So three tables will be clustered around one common primary key. So then the searches are much faster in a table cluster because the primary key is shared between different tables. So query performance is definitely really good. So what I've done today is focused on the storage management clause and also talked about working with table spaces and different types of partitioning. You can use this information in assignment 7 for the second part. So for the first part I helped with last week. So this week we have spent time on understanding the the different partitioning types. So you have to project which tables will increase quickly and implement the partitioning type for at least 2 tables in your database schema. And what I do want you guys to do is rationalize the choice of the partitioning type. So for example, if you end up using partition by range, you might say that we are going to do a lot of student enrollments. So looking up data by student ID rationalizes the usage of partition by range clause. Or alternatively, if you end up using partition by list and you're trying to separate data between 2 colleges or multiple colleges, so then you use college name for list partition. Any questions so far, people, that I can probably help address for lab 7? Or everyone is doing okay? Give you guys a minute to think about that, and then we'll continue to the next topic. Okay, so the next thing we have to focus on is creating indexes. This is something you guys are going to end up using in assignment 8. So index is also a schema object, and it's generally created so you can increase the speed of data retrieval. So how would an index enable you to do that? Well, just like in the back of your book, you have an index that takes each concept and refers to it refers to the page number. Like that, in a database index, you have the rows referring to a specific row ID. Each row ID sits in a data block, and information about the data block and the row IDs is in the data dictionary. So we look up the data dictionary and we know exactly which block to go to fetch that row. So as a result, we reduce the disk IO, and the indexes apply to all table types. It doesn't matter, they're kind of independent of each table that we create, although an index is always associated with a table. And indexes are automatically managed by the database, unless of course you turn off that database management. So when you have a primary key or a unique key, we create index automatically, or we can create an index manually using the create index clause. Something like this. You can index more than one column. How do you decide which columns to index? So when you can basically say which columns are being queried the most, and you can use that as a basis for querying the indexes. So like here we are creating an index on employee name. This is when to create indexes and this is when not to create indexes. So there are like 5 areas that are specified, and the inverse is for when not to create indexes. So if you are fetching small amounts of data, like less than 2 to 4%, it's good to create an index. So in lab 8, you're going to be asked to choose tables for creating indexes. These 2 slides, when to create indexes and when not to, are going to be the most useful for your purpose. So please put your analysis through these 2 slides when choosing the tables for creating indexes. The next thing is, what data dictionaries do you use to find index information? So we have one called user indexes that tells you what indexes exist in the database. And then the other is user index columns. That tells you what columns to put, what columns are indexed. So sometimes we write queries in the where clause where we try and we use we use functions, or we might have some expressions in the where clause. As you might imagine, doing that in a query can get very expensive. So if we can pre-compute those values with function-based indexes, the queries will be much faster. Look at the create index called test index, where we add the value 10 to column 1. That is a function-based index where we just add the value 10 to column 1. So when we now do a query, we are just going to check the index for values and not even go to the table. And that will make the query results really, really fast. So function-based indexes. Dropping an index is pretty easy. We just drop the index. That'll remove it from the data dictionary. Then we have indexes that can either be unique or non-unique. Whenever we have a primary key, we create a unique index. Basically, no duplicate values. Non-unique, on the other hand, can have duplicate values. Does not impose any restriction on the data columns. Unique indexes have to be created explicitly. If a column has any kind of a unique constraint, a unique index is created. Null values are considered to be unique with unique indexes. Null values are considered unique. So be careful about this for test questions, please. How are indexes stored? So those of you who are interested in index storage will find this very useful. Indexes can either be saved as B trees or bitmap. And we can also have bitmap join indexes. So this is what a B tree looks like. Like a little tree structure. So, and then the tree structure is organized into lists. Bitmap index, on the other hand, is used when you have a lot of less unique values. Like this. Say, using it for like marital status or gender or the region where a person lives. And this allows for faster queries when a bitmap index is used. So we can basically in a bitmap index have specific columns for each unique value. So east, central, and west, for each row in the table, when I index, I can create a bitmap for the region. So if somebody is in east, the value of that index will be 100. Similarly, if somebody is in central region, I will set the value to 010 and so on. So then we can use bitmap indexes when joining data. So like we can have, where marital status is married and region is central or west. So we can do binary math essentially. Yeah, we can do binary math and compute the specific results. So this improves query performance significantly. And that's where we do bitmap joins, where you create two or more tables with a join, and because we are saving data in binary, the storage space, it doesn't take that much space in memory either. So different index types. And this basically tells you how bitmap indexes actually work. So we end up with a query like you see below, and how the bitmap index is created. We actually have to use a formal label name to specify an index is a bitmap index, and generally created between database tables that have primary key and foreign key. So we've talked about different types of indexes today: unique, non-unique, bitmap, and just like we talked about database partitioning, table partitioning, we can also do index partitioning. And the different partitioning types that we talked about for table, range, hash, and list, they apply for index partitioning as well. So we should talk a little bit about that as well. As long as we are on the topic of partitioning, we should go over that. Like, what is index partitioning, and when should index partitioning be used? Can everyone still hear me okay? And are there any questions you guys may have? So, review of partitioning concepts. We use it on partition tables. There are different types of partitionings, and when we can partition using more than one column for any of the types that are mentioned here: range, hash, list, or composite. And times when partitioning should be used. All types of table partitioning are used for index partitioning as well. So the idea of this slide deck is really to show you how index partitioning is applied on tables. How index partitioning is applied on tables. So again, why use partitioning is expressed in this, but these are local partition indexes. So the local partition indexes stay in the same table space as the table partition. So you have a partition table with different partitions in different table spaces. We can create the index partition in the same table space. The syntax for creating a index partition is shown below. We basically say create index on employees local, and we're done. We can also have a global partition table, which is really a waste of time because of the cross linkages will lead to poor performance. So I can have a partition table, and when I do a global partition table or a partition table that is global, it will have its own partitioning algorithm. And then we'll have these cross linkages that will take forever for query processing. So not advised for usage on large data sets. Global index that is not partitioned is a good idea. But if the table gets too large, that will slow down performance as well. Here is how a global partition index can be created. It has its own partition by range clause. And if you just want to create a global index without partitioning, then we just create a regular index on a partition table. Indexes have to be maintained, and these are all the operations that can be applied on an index. Rebuilding the index, adding a new partition, removing a partition, removing free spaces, exchanging two partitions between table, merging a partition, moving a partition from one table space to another, splitting it, or emptying the data out of a partition. These are all the index operations that can be carried out on a table space. Then we have index dictionaries, where we can find index operations, index information, excuse me. If we want to figure out how the indexes are used, indexes take up memory. So you want to monitor the indexes to ensure the index is being used or not. So we can turn on monitoring It will collect some statistics, and then we can look at those statistics to see if an index is indexed. If an index is being used or not. If an index memory is not being used, we don't want to use the memory for that index. However, if it has good usage, then we keep using it. So you all can finish lab 7. And the fact that we have already talked about the DML statements, you can also start working on lab 8. So assignment 7 is due in a day, but 8 is due on 23rd. In assignment 8, you are being asked to use DML statements to set up a department, create a course with 2 sections, and a section with a location. And then you have to produce a report showing the department, its courses, and sections. That's like a small catalog report. You can actually use the view for that. Then you register a student and process student payment and show a report showing the registration information with the payment information. All of these can be written in a nice SQL script. So then you have to make recommendations on how you can improve the database schema further, and that's where you can say we can add indexes on this and that and things like that. So you make a list of those 4 for getting full points on lab 8. I've provided a reference to these 2 documents so you can use those in lab 8. Okay? I think next time what we're going to do is spend time looking at the database utilities and database security. We'll do that on the 20th. And if there are any questions, of course, please let me know and I'll gladly answer those for you. This is all I have for today, folks. Have a great rest of the Tuesday, and I'll see you all next time, same place. And we are going to have our final on June 27th, I believe. So just to double check the date before we go, so we at least have a little, you guys have a little headlight visibility on when the final is. It will be on June 27th, Tuesday from 9 to 10:30, which is about 2 weeks from now. So everyone have a great day. Bye now.